and 1. All right. And then here are our response. Oh, look at that. That's beautiful. Look at that. Okay. More than 90% answers for sure. Okay. 95% select the correct answer. Very good. Okay. Now, again, just to remind us about, I have like few people selecting here and there, some other answers as well. So just to bring everybody to the same page, okay, in the PEC diagram, we have the potential energy axis and the number of configurations axis. And if you consider these two states, S1 and S2, in S2, we have particles far apart from each other, meaning they're going to have weaker attractive interactions between the particles. Weaker attractive interactions between the particles, high the potential energy. Okay, and that's why we place S2 at a higher level in the potential energy axis. Okay, and then when it comes to number of configurations in S2, the particles are not attracted to each other. They have more freedom to move around. They're like singles. Okay, so as a result of that, they're going to have more configurations, more number of configurations in S2. Therefore, S2 should be towards your right with respect to S1, and that's why option D is the correct PEC diagram for this question. Do we have any questions, concerns, comments at the moment? Anything? Any questions, concerns? Yes, miss. Yeah, diagram. Yeah, the question is, will there be any situations like where we can have like C or B or D? Yes. All of these are possible scenarios for any process. Yes. Yes. Okay. Now, I mean, especially if you have a PEC diagram like A or C, okay. I don't know. I wasn't planning on mentioning this now, but I mean, why not? Okay. So in the PEC diagram, I have corners here. Okay. I divide my PEC diagram into corners, like 4 quadrants. Okay. So if you're in this corner, I call this the nice quadrant or the nice corner. Okay. If you're here, both mom and dad love you. Okay. You're always favored. Okay. Because both potential energy and number of configurations favor you. Because potential energy is lower, number of configurations is higher, so you're always favored. Okay. And then on the other hand, the quadrant diagonal to that is this quadrant over here. This is called anybody? What do we call this corner? The naughty corner. Right? If you are in this corner, both mom and dad hate you, you are never favored. You are doomed for life. Okay. And then we have these other corners here, like, these other quadrants over here. Okay. In this case, the number of configurations is favoring you, but the potential energy is not. Okay. Mom loves you, dad hates you. Okay. So your existence or your favorability is contingent upon other things. Okay. And the same thing when it comes to something like option B, like for an example, if you are in this quadrant over here, okay, now the dad loves me, but mom hates me. Okay. If that is the case, again, I mean, it depends on, like for example, temperature, whether you are favored or not. So those are the quadrants. So the naughty quadrant and the nice quadrant are the best ones, easiest one for us to remember. The other ones are dependent on the temperature mainly. All right. Do we have any other questions, concerns, comments at the moment? Anything? We'll talk about this temperature dependence in a second, okay? Give me a second. Let's do this. Why not talk about temperature dependence now? Okay. Here's the same PEC diagram we came up with before. What I want you to do is, I want you to tell me if we increase the temperature, what state, S1 or S2, will be favored. So one of the usual questions I get from here is, what do you mean by favored? Okay. That is more probable. Okay. More likely to occur. Okay. At higher. The microphone with Annie, please. I'll take it. All right. Here you go, Annie. Annie, go ahead. Why do you think S2 will be favored at higher temperatures?
Because when you increase a temperature, S2 is a gas, and so when you increase the temperature on something like a liquid, it boils and turns into a gas.
Okay, that's by analogy. But looking at these two states, right? Okay, that's okay. Now, what can you tell me about the S2 potential energy? Is it higher or lower?
It's higher.
It's higher, right? So higher means, do we have stronger interactions or weaker interactions?
A week.
Weaker interactions. So the idea is when you increase the temperature, you are increasing what energy?
Kinetic.
The kinetic energy, meaning the particles are moving faster. Guess what? When the particles move faster, you cannot have stronger attractive interactions. Okay. In other words, when the particles are moving faster at higher temperatures, it favors or it promotes the state with higher potential energy because it is promoting the state with weaker attractive interactions. Yeah. So that's why increase in temperature will favor the state with higher potential energy. Can you make a note about that? Okay. High temperatures favor the state with higher potential energies. Okay, let's do this here as well. Option C, and that's the correct answer as well. All right. Do we have any questions, concerns, comments at the moment? Anything? Any questions, concerns, comments? Okay. I'm going to come back to this as well. Just to summarize at this point, okay, when it comes to the potential energy axis of the PEC diagram, that is governed by temperature. Okay. So higher temperatures favor the state with higher potential energies, and lower temperatures favor the state with lower potential energies. And that is what is mentioned in this slide as well. All right. Do we have any questions, concerns, comments? Now, please remember, I know that, I mean, it's not totally incorrect that the higher temperatures might facilitate the state with higher number of configurations. That is okay. But the thing is, empirically, by observing many experiments, we've seen that the link of temperature to the potential energy is more significant than to the number of configurations, and that's why we are saying that the potential energy axis is governed by temperature, not the number of configurations. All right. To the same thing, I want to talk about the same thing one more time with the number of configurations. Okay. So as I mentioned, number of configurations axis is governed by pressure. Okay. So let's think about this. If you have a higher pressure, will it favor the state with higher number of configurations or lower number of configurations? One more time. If you have a higher pressure, will it favor the state with higher number of configurations or lower number of configurations? Everybody. Thank you. Lower number of configurations. Higher pressure means you're going to have more restrictions to move around, meaning you're going to have less ways of arrangement. That's why high pressures favor the state with lower number of configurations and vice versa. Okay. So now we have those two down. What I want to do is we're going to start applying them. Okay. Let's start with this. All right. More than 90% at this moment. So I'm going to close this question in 5, 4, 3, 2, and 1. All right. And then here are our responses. Okay. Most of us said at lower pressures, okay, S2 will be favored because the lower the pressure, the more configurations the particles can adopt. And that's the correct answer as well. Again, temperature, we are linking with the potential energy, and the number of, and the pressure, we are linking with the number of configurations. That's the whole point of these activities, and the last two activities. Okay, now let's start applying this. Here we go. Here are two allotropes of carbon, okay, diamond and graphite. Okay. What I want you to do is, in your groups, I want you to answer these 3 questions. Go ahead. So which state or which allotrope of carbon is favored by potential energy? What do you guys think, everybody? Okay, those are the options, diamond and graphite, but which one is it? I heard that, but which one is it? Which one is favored by potential energy? Thank you, graphite. Why? It has a lower potential energy, okay? The state with lower potential energy is favored by the potential energy because everything happens to minimize the potential energy. Okay. And what about the number of configurations? Which state is favored by the number of configurations? Diamond or graphite? Graphite again. Why? Why? Why does number of configurations favor graphite? Anybody? I know you know it. You can say it. It's okay. Say it. We can say it. Say it. Just kidding. All right. Yeah, Teresa, why? Yeah, no, we don't have the pressure information yet. So number of configurations wise, graphite is favored. Why? It's higher number of configurations. Okay, because everything happens to increase the number of configurations or maximize the number of configurations. And that's why your dorm room is going to get messier and messier and messier with time. Number of configurations, blame the nature. That's the nature. Okay, now anyway, so graphite is favored by both potential energy and the number of configurations for that reason. Okay, so any questions about that? Anything? Okay. Now, the second question is, what changes would you expect to see when the temperatures increase? What do you say? If you increase the temperature, what do you expect to happen? Colin, I know that everybody wants to speak. Give the microphone to gentlemen from this table. I know anybody from here. Yeah. All right. So if you increase the temperature, what do you expect?
Diamonds.
Thank you. Tell me what. That's perfect. Tell me why though. So you expect the diamonds to be favored more. Why?
Because the potential energy goes up.
It's perfect. It's not perfect. Potential is going up, but increasing temperature will, okay, this is the way you should answer your pre-response questions. Increasing temperature will favor the state with higher potential energy. Meaning weaker interactions. Okay. So that's why increasing temperature will favor the formation of diamonds. All right. What about the pressure? If you increase, what would you expect to see when the pressure is increased? Anybody? You can give the microphone to anybody from there. Okay, yeah, that table. What's the name, sir?
Ethan.
Ethan, what do you expect to see? If you increase the pressure, what do you expect to happen? Will it form more graphite or more diamond?
If you increase the pressure, I'd expect more diamond.
Diamond form, I agree. Okay, but why though?
Because.
And pressure is related to which axis? Potential energy or number of configurations?
Configuration.
No, thank you. Number of configurations. So increase in pressure will favor the state with higher number of configurations or lower number of configurations?
Lower
number of configurations. Diamonds have a lower number of configurations, and that's why increasing pressure will favor the formation of diamonds. Okay, so in fact, that is exactly how the diamonds are formed, like synthetically. Okay. Now, do we have any questions? Okay. Now we got that. Let's do one last practice problem with that. Okay, this one, maybe two. All right, and then here are our responses. Look at that, it's beautiful. Most of us selected option C, and that's the correct answer as well, almost 90%. Okay, anyway, so what conditions favor the formation of S2? S2 has a lower potential energy, meaning lower temperatures will favor the state, S2 state, or the diamonds. And also S2 has a lower number of configurations, meaning if you increase the pressure, increasing pressure will favor the state, favor S2 because it has a lower number of configurations. Okay. And that's how we answer that question. Do we have any questions, concerns, comments about that? Anything? Any questions, concerns, comments? Okay. So these are the questions that we can expect in an exam or a quiz as well. You can be given a PEC diagram and be asked what conditions will favor the formation of one state over the other. Okay. And then you think about the temperature and pressure and then why. Okay. And then if you're thinking about temperature, look at the potential energy axis. If you're thinking about the pressure, look at the number of configuration axis. Okay. All right. This is the way. All right. Now, let's do one last question, I think. they're representing the process of boiling here. Okay. And then up over here, what phase are we representing here? Anybody? Thank you. The gas phase. And down over here, what do we have? The liquid. Thank you. Okay. So you see that in the gas phase, the red particles or the red substance and the blue substance is overlapped with each other, meaning in the gas phase, you cannot distinguish which one has a higher potential energy or lower potential energy and higher number of configurations or lower number of configurations. They're the same in the gas phase. That's what they're trying to denote here by overlapping these two states, these two diagrams. Okay. And then on the other hand, when it comes to liquid, okay, you see a clear difference. Okay. So the clearest difference is the potential energy. Okay, which particles have a lower potential energy, red or blue? Everybody. Thank you. Red has a lower potential energy. That means it has stronger attractive interactions or weaker attractive interactions. Thank you. Strong attractive interactions. If you have strong attractive interactions, should it have a higher boiling point or lower boiling point? Higher boiling point. Okay. Out of the two substances, oxygen has a higher boiling point. Therefore, red should correspond to oxygen. That's how we arrive at the answer. Yeah? All right. What questions, concerns, comments do we have at the moment? Anything? Any questions, concerns, comments? All right. So, particles, something like that. You can do that.
Oh, okay.
Yeah. Yeah.
Okay. Thank you.
Yep. All right. Do we have any other questions, concerns, comments at the moment? Anything? All right. So these are the types of questions we can expect from PEC diagrams, reading PEC diagrams and identifying which one has higher or lower potential energies. Based on that, linking that to the strength of interactions between the particles. Okay. And then relating that to properties like boiling point, melting point, condensation point, sublimation points, and so forth. All the same thing, in a way. All right. So, yeah, looks better. Now, at this point, okay, we are done with Unit 1, Module 2. What I'm going to do is I'm going to give you a preview of coming attractions when it comes to Unit 1, Module 3. Okay. So in Unit 1, Module 3, what we're trying to do is, okay, remember we used a model in Unit 1, Module 2 to explain what we saw, the differences we saw in Unit 1, Module 1. So now what we're going to try to do is we explain these differences considering the third assumption of the particulate model of matter. That means particles interact with each other, stronger the attractive interactions. Okay, high the boiling point, high the melting point, high the density, high the viscosity, and lower the wave pressure and lower the volatility and so forth. We explained it. Okay, but here's the thing. Are you satisfied with that? Do you have any other questions about it? Or are we done? We're never done, right? We're never done. Okay, so the question a scientist asks is why? Okay, why some substances have strong attractive interactions while the others have weak attractive interactions? Okay, to answer this question, we need to zoom into the particle, okay, and then see what the particle is made of. Okay, so to do that, we're going to use another model. We call that the atomic model of the particle. Okay, meaning the particles are made of atoms. That's it, simply. That's it. All right. So that's what Unit 1, Module 3 is about. Now, I mean, it's a very straightforward module, at least the first part, until you have to do calculations, based on my experience. But anyway, so that's going to be the second part. But first part is very straightforward. Let's look at this. Okay. Question number 1. How many different substances do you see in the system? Okay, go ahead. All right, I think we already have more than 90% answers, which is great. I'm going to close this question in 5, 4, 3, 2, and 1. And then here are our responses. Look at that. Okay. Almost everybody agrees, almost everybody, okay, that there are 5 different substances here. 98%. How do we know that? Anybody? How do we know that we have 5 different substances here? the composition of the particles, right? Yeah. So look at this. All right. So we have like two blue atoms bound to each other. So that's one type of particle, one substance. You have this guy over here. By the way, what is this? Anybody? What do you think this is? That is not oxygen. Thank you. That's nitrogen. Okay, that's very good. Nitrogen. And then what about this? What is this guy over here? Yeah, water. Okay, we have H2O or water. Okay. And then what is this guy over here? CO2, carbon dioxide. Okay. And then what about this guy over here? Does anybody know what this is? It's a different particle for sure. It's called benzene. You might have seen this. It's a very famous structure, actually. It came to Kekule or somebody in his dream, like how this is connected to each other. Anyway, that's a different story for another time. All right, that's called benzene. And then we have another particle over here. That's the fourth one. Okay. And that is, I believe, normal pentane. That means C5H12, I think. Anyway, it's a different particle. That's all that matters. All right. So those are the 5 different particles we see, different compositions of the particles we see, meaning we have 5 different substances in the system. All right. Do we have any questions, concerns, comments at the moment? Anything? Any questions, concerns, comments? All right. Now, with that, what I want to do is, I feel like I want to do this in my notebook though. Let's see. All right, let's do this. Okay, I'm going to switch to my notebook for a second. Okay, really quickly. Okay, so when it comes to matter, all right. So when it comes to matter can be pure substances, or they can be mixtures. Okay, and the mixtures can be homogeneous. So inhomogeneous based on the composition from the place to place. We will not talk about mixtures. I mean at this moment, but okay, there's something else going on with mixtures as well. And when it comes to pure substances can be elementary substances, or they can be compounds. Okay, and examples for elementary substances are like, I don't know, let's say helium, neon, argon. These are monoatomic elementary substances, or they can be hydrogen, nitrogen, oxygen. Okay, diatomic, you have 2 atoms bound to each other. Okay, elementary substances, or they can be something like P4, phosphorus, and then S8. Okay, so and so forth. Okay, the idea is you only have one type of atom in them. That's why we call them elementary substances. Okay, and then when it comes to compounds can be covalent, or we also call them molecular. Okay, or they can be ionic. Okay, so when it comes to compounds have more than one type of atoms bound to each other. Okay, for an example, carbon monoxide, water, okay, and then sulfur dioxide, and then NO2. Okay, you see that you have more than one type of atoms bound to each other. Okay, that gives rise to a compound, and these are covalent compounds because these are made of only non-metallic elements. On the other hand, we have ionic compounds as well. Does anybody know an example for an ionic compound? Yes, miss? NaCl or table salt, right? Okay, NaCl, sodium chloride. And then if you go to, if you have been to a beach, you have seen seashells, which are made of calcium carbonate. And then we have magnesium nitrate, you might find them in your fertilizers. It should be 2. And then there are some other fertilizers like which contains ammonium. Let's say ammonium nitrate again, NH4NO3. It's an ionic compound. Okay, so these are like different ionic compounds you can find, in our day-to-day life. All right, so this is called classification of matter. Okay, they can be pure or mixtures. Pure can be elementary substances or compounds. Elementary means they are made of only one type of element or atom. Okay, and when it is compound, if it is a compound, compounds are made of more than 2 or more types of atoms. Right, and then compounds can be covalent or ionic depending on their nature. Covalent compounds have covalent bonding, and ionic compounds have what we call ionic bonding in their structures. But we will not talk about ionic compounds until Unit 3, Module 3, which is like the 4th exam. So yeah, we have a long ways to go there. Get that. All right. Do we have any questions, concerns, comments at the moment? Anything? Any questions, concerns, comments? Yeah? Okay. So that's that. All right. I'm going to go over the next few slides very easily like this. Okay. Elementary substances examples, they can be atomic, like argon. Okay, this is the macroscopic representation, and the particulate level, you just draw atoms, and the atomic symbol is Ar. And it can be like diatomic or molecular elementary substances like nitrogen. Okay, and this is how we represent nitrogen. By the way, we have a liquid nitrogen duel, like a huge thing, like by the Marvel building. If you haven't seen it, you should go there and check it out. It's very cold. Anyway. That's about elementary substances, and then all these elementary substances are made of elements that can be, found in a table called the periodic table. Okay, if you don't have a periodic table yet, you should have one. Okay, you should have one on a T-shirt or maybe, as a poster in your dorm room or something like that. If not, at least in your pocket. You're gonna need that as people studying chemistry. It's a beautiful representation of like how the elements interact with each other as well. We'll talk about them a little bit later. All right. Now, and that brings us to chemical compounds. Chemical compounds can be like molecular, like carbon dioxide and H2O. Okay. Or they can be ionic. We don't have the ionic example here, but yeah, if it's ionic, something like sodium chloride and calcium carbonate and things like that. All right. Now, with that, what I want you to do is I want us to try this question. Go ahead. I want you to identify them as elementary substances, compounds, or mixtures. Go ahead. All right. I'm going to close this question in 5, 4, 3, 2, and 1. All right. And before I look at the answers, I'm going to quickly do this with you. Okay. So the first guy over here is anybody? First one. What is it? Thank you. It's a chemical compound. Let's call it CC. The second one over here is elementary substance. I think this is fluorine. They're trying to denote fluorine here, F2. So by the way, so chemists use like different colors to, represent different atoms. For example, red is for oxygen, and then black is for carbon, or black or gray is for carbon, and then blue is for nitrogen, and then white small ones are for hydrogen, and so forth. Okay, so it's good to know, but in a printed exam like type B exams, they're not going to print you like colored, pictures. So don't worry about the colors there. But anywhere else, you should be able to identify them. Anyway, the third one over here, what is it? Yeah, it's elementary substance. It's carbon, by the way. I think it's representing diamond over here. And then what about the fourth one over here, down here? Yeah, it's a mixture. Okay. What about the fifth one over here? It's a mixture as well, because we have oxygen with water. And what about the last one over here? Yeah, it should be a chemical compound. All right. I have a feeling that not all of you identified the fourth one as a mixture. Okay. We have these particles over here, which is ammonia or NH3. And also we have these particles over here, which is hydrazine, which is used as a rocket fuel, which is a different substance. So it's a mixture of substances. All right. Do we have any questions, concerns, comments at the moment? Anything? Okay. All right. I'm going to clear my doodling. All right. Look at your responses. Okay. Two different answers. Okay. By the way, I will reopen the question in case you want to revise your answers. All right. Now, let's do one last thing. Here we go. Maybe two things, two other activities, and we're done. By the way, this compound. All right, I have more than 90% answers now. I'm going to close this question in 5, 4, 3, 2, and 1. All right. So let's look at this. Right. How many phases in the system? Oh, that's the one. Ah, we start with that. How many phases? What do you think? You know what? Don't tell me. I got your answers here. Oh, look at that. Okay, most of us said 3. Do you agree with that? We had 3 phases. Yeah, I hear both. Yes, no. Yeah, okay. So here's the thing. Now I know that why. I mean, if you don't agree, I know why. Okay, you're not used to seeing like liquids. Okay, like in this case, all right, you can see that we have 2 different liquids. Okay, we have water at the bottom, and then on top of that we have like an oil layer, like floating on water. All right. Whenever we have 2 liquids that are not miscible, that are not mixing with each other, those 2 liquids are considered as 2 separate phases. Okay. So in liquids, we can have different phases. If they don't mix, those are 2 different phases of liquids. Okay. Just like when you mix oil with water, you see that they are going to separate into like an oil layer and the water layer. Those are considered 2 different phases of water. Okay. For that reason, we have 2 different liquid layers and the gas phase. So therefore, we have altogether 3 phases in this sub-microscopic representation. Right. Now, any questions, concerns, comments about that? Anything? Okay. Now, that is that. And then we have, let me see, how many different substances in the system? So we can count them. We have oxygen, nitrogen, and then pentane, and then water, maybe 4. That's right. How many different elementary substances are there? We have nitrogen and oxygen, just 2. How many chemical compounds in gas phase? We have none in the gas phase. Okay, nothing, no chemical compounds in the gas phase, and that is correct as well. All right. Do we have any questions, concerns, comments at the moment? Anything? Okay, last question maybe for today. All right. Let's do this.